Hello, I'm Dr. Maurice Dupre, and in this section we're going to discuss substitution and area between curves. Substitution is a very useful technique for computing integrals, both definite and indefinite, and we're going to begin by looking at substitution in definite integrals. Substitution in definite integrals. If g prime is continuous on the interval close bracket a comma b close bracket and f is continuous on the range of g, then the definite integral of f of g of x multiplied by g prime of x dx equals the definite integral from g of a to g of b of f of u du. So in effect, we're replacing the g of x in this expression by u, and then the g prime of x dx becomes the du. One thing to keep in mind here, when you see this in practice, you're going to be looking for a function of a function, some type of grouping symbol, say a radical or parenthesis with an expression inside, and the derivative of that expression somewhere else. So for instance, this g prime could be over here in front of the f of g of x as a factor. It would still give the same equation. Also, if the derivative only appears up to a constant factor, because constants can go in and out of the integral sign, that can be adjusted, and we'll see how this works in practice. Well, let's look briefly and see why this is true, because it's such a simple consequence of the chain rule for differentiation. Remember, any rule for differentiation is going to give us some kind of rule for anti-differentiation or integration. In this case, let capital F be any function whose derivative is little f. And let's consider the function capital F of g of x. What happens when we differentiate capital F of g of x by the chain rule? Well, notice the chain rule says differentiate the outer function, putting in the inner function. Well, the derivative of the capital F is the little f. We leave what's inside alone, and then multiply by the derivative of what's inside, g prime of x. And so that would tell us that if I want to find the antiderivative of f of g of x multiplied by g prime of x dx, it is simply capital F of g of x plus constant of integration, of course. In other words, the anti-differentiation process for anti-differentiating f of g of x times g prime of x dx is simply solved by anti-differentiating the outer function. The inner function g of x, notice, is just going along for the ride. Well, what's going to happen when I compute the definite integral? I have to evaluate. In other words, if I want to compute the definite integral of f of g of x, g prime of x dx from a to b, that just simply means evaluating this capital F of g of x between the limits a and b. But notice, when I substitute the upper limit, I get f of g of b. When I substitute the lower limit, I get capital F of g of little a. And so consequently, that's the same as evaluating f itself, that's the capital F, between the limits g of a and g of b. And it doesn't matter what symbol we use for the variable in this capital F. So we could pick anything, say u, v, w, whatever. We call variables like that dummy variables because in a sense it doesn't matter what symbol you choose. So when I evaluate the capital F between g of a and g of b, well, remember capital F is the antiderivative of little f. So in effect, I'm just taking the integral of little f from g of a to g of b. So the end result of this is we have this equation, which I've written out here again in two lines. Notice the integral from a to b of f of g of x times g prime of x dx is the definite integral from g of a to g of b of f of u du. Now when I look at it like this, what I want to do is point out a kind of a notational procedure which will make this process computationally effective. That is, we turn it into a procedure. And so when I spot this situation, what I will do is say, well, let's substitute a single symbol, and we'll usually choose a U to begin with. If U is already in use, we'll pick some other symbol, but I'm going to set U. I'll draw a vertical line here, and I'll set U equal to g of x. Once I've done that, then du is equal to g prime of x dx. So in this equation here, you see, here is right here. That's going to become just u, f of u, and all of this is becoming the du. And so notice in the replacement down here, the f of g of x becomes f of u, the g prime of x dx becomes the du. And what about our limits? Well, we are now integrating with respect to u, so in a definite integral we have to put our limits in terms of u. Well, when the lower limit of x equals a, u is g of a, and when we get to the upper limit for x, b, u is g of b, and so that's why the new limits are now in terms of u, g of a to g of b. So that's the procedure. When you're dealing with a complicated integral and you think you have a substitution which you want to try, come over here, draw a vertical line, and set u equal to that expression in terms of x. Then calculate du, and then look to see to rearrange the integrand so that you can get the g prime of x paired with the dx, and then you're going to substitute du for all of that, substitute u for the expression that you set it equal to, and then you've simplified your integral. But then before you go any further, you have to change the limits. You have to remember that once in a definite integral you've made the replacement u equal g of x, then your lower limit is g of a and your upper limit is g of b, where a and b were the original limits on x. Well, the notational procedure I've just described, of course, isn't absolutely necessary. You can develop any notational technique you like, but I would advise you to strongly consider adopting the one that I'm using here. It's used in virtually all mathematics books and physics books, and it's very common, and it's been proved over time to be very effective in computations of integrals. Here in this problem, I want to compute the definite integral from 0 to square root of 3 of the quantity 4x divided by square root of x squared plus 1. So we look at this expression and notice integrating square root of something nasty down there looks like in general we've got trouble. So what I would like to do is just have simply a square root u down here. That would be nice. And so let's take a chance and try the substitution u equals all of x squared plus 1. Now the first thing I'll do is compute du, which is the derivative of u with respect to x multiplied by dx. Well, the derivative of u with respect to x is simply 2x, and so du is 2x dx. We don't have a 2x up here in the integrand, but we do have a 4x, and so what I can do is rewrite that 4 as a 2 times 2. For instance, I can say, well, this 4 is, cross it off and put 2 times 2, and now notice all of this dx times the 2x is our du. That will be replaced by du, and this radical down here just becomes square root u, and we have left the 2 up in the numerator. The other thing we have to remember to do is change our limits. So we'll begin by writing this equals definite integral, and now what are our new limits? When x is 0, u is 1. When x is square root 3, u is square root 3 squared plus 1. Square root 3 squared is 3, plus 1 makes 4. So now we have our new limits, definite integral from 1 to 4, our numerator 2 divided by square root u, and all of this is just du. Well, so that's an easy one to do. Notice we can take the 2 out as a factor out front. We're finding the antiderivative then of simply u to the negative a half, which is simply u to the plus a half divided by a half. And that's to be evaluated between the limits 1 and 4. Of course, a factor of a half down in the denominator amounts to an effect of 2 up top, so 2 times 2 is 4, and we end up with 4 square root u to be evaluated from 1 to 4. So that's easy enough to do. We begin by putting 4 into the square root, and that's square root 4, or 2, minus what we get by putting 1 into the square root, which is of course 1. 2 minus 1 is 1, and so the final answer in this case is simply 4. Well, let's look at another problem of substitution where we now have different limits of integration with the same integrand. Remember, the substitution process involves not only the integrand, but the limits as well when we're dealing with definite integrals. So here we have the definite integral from negative root 3 to positive root 3 of the same integrand, 4x divided by the square root of x squared plus 1, and we know already to substitute u equals x squared plus 1. But now what are our new limits? When x is negative root 3, u is negative root 3 quantity squared, well, that's 3, plus 1, which is 4. On the other hand, when u is positive root 3, we get the same thing, 4. And so our new limits of integration are 4 to 4. And here, without even working it out, we know that's 0 because the lower limit and the upper limit are the same. And now let's look at a problem where the integrand involves trig functions. Many useful substitutions are done with trig functions because they have such nice identities. At this time, why don't you pause the video and try this problem on your own. Here I want to integrate from 0 to 2 pi the integrand cosine z divided by square root of the quantity 4 plus 3 sine z dz. So again, when I see this big expression inside the radical, the first attempt would be set u, what's inside, equal to what's inside. U equals 4 plus 3 sine z. In that case, du is the derivative of this quantity, 3 cosine z multiplied by dz. Now I look up here in the integrand, and I see a cosine z, and that's enough because the 3 is easy to make. All I do is put a 3 in front of the cosine and a 1/3. Notice they cancel, but now I can group this all together to make the du. And so this becomes then integral. New limits, what are our new limits? When z is 0, sine of 0 is 0, and u is just 4. When z is 2 pi, sine of 2 pi is 0 again, and this is just 4. And so we know our definite integral from 4 to 4 is 0, but on the other hand, notice that we can still go through the substitution for practice. It's a useful exercise to see what integral we would have gotten. So this 1/3 can come out front. All of this is du, and down here we have square root u. So you see, that's a nice simplification of the integrand. And if the limits had been different, we wouldn't have necessarily obtained the same limits for lower and upper limits on our definite integral. But in any case, integrating from 4 to 4, we know that's 0. Again, let's look at a different pair of limits on this same integrand for a definite integral. Same integral, cosine z over square root 4 plus 3 sine z, but this time let's do the definite integral from negative pi to pi and see what happens. So u is 4 plus 3 sine z du is therefore 3 cosine z dz. And so we're going to get, putting in a 1/3 times a 3 into our integrand, 3 cosine z dz is our du. So we have 1/3, which can come out, definite integral du divided by, and of course all of this inside the radical is now just u, square root u. What are our new limits? What is the sign of negative pi? Well, that's 0. What's the sign of positive pi? Again, that's 0. So we have the definite integral again from 4 to 4, and so again we get just 0. Well, we know that the definite integral corresponds to area when the function we're integrating is always greater than or equal to 0. That is, the definite integral from a to b of a function f greater than or equal to 0 gives us the area under that curve between the limits x equal a and x equal b. In many actual applications to finding areas, though, the region we want to find the area of will be described by functions which aren't necessarily above the x-axis, and we may have a region enclosed by various different graphs. So we want to begin by trying to write down how we find the area between two curves. Area between curves. If f and g are continuous with f of x greater than or equal to g of x throughout the closed interval a comma b, then the area of the region between the curves y equal f of x and y equal g of x from a to b is the integral of f minus g from a to b. So for instance, in symbols, that's capital A for the area equals definite integral from a to b of bracket f of x minus g of x close bracket dx. And so the picture you should have in mind here is that here you have two curves, but in this case the fact that f of x is greater than or equal to g of x means that the graph of f is always above the graph of g. And here we have the vertical line, maybe x equal a, and here's the vertical line x equal b, and what we want to do is find this area between these two curves. And notice the distance, the vertical separation distance at a given x here, this distance right here, is the f of x minus g of x. And so consequently what we're doing is integrating this vertical separation distance from the left limit to the right limit, and now it does not matter where the horizontal axis is. The horizontal axis could be up here, here, or here. It doesn't matter. It only matters that f is above g. Now let's work a problem where we actually calculate the area between two curves where one of the graphs is above the other. Okay, here I have two curves shown. The top curve is the parabola y equal 2x squared, and underneath we have this fourth degree curve y equal x to the fourth minus 2x squared, comes down and actually dips below the x-axis, comes back up at the origin, then dips back down, comes back up. And these two curves intersect at the points -2, 8 and 2, 8. And obviously they're enclosing some area that's shaded here in the picture, and we'd like to find that area. So here I've drawn the picture again just schematically, and notice throughout the interval -2 less than or equal to x less than or equal to 2, which is the entire range of x values we're concerned with here, the curve 2x squared, y equal 2x squared, is above y equal x to the fourth minus 2x squared. That is, 2x squared is greater than or equal to x to the fourth minus 2x squared, and so consequently that area is the definite integral from -2 to 2 of the quantity 2x squared minus the quantity x to the fourth minus 2x squared. And so that's all we do is calculate the definite integral from -2 to 2 of this integrand. Well, the first thing to do is actually simplify the difference here. Notice negative 2x squared is another positive 2x squared, so really altogether we have here 4x squared minus x to the fourth, and so there is a simplification of the integrand. So we've turned our problem of computing the area actually into the calculation of a definite integral, which is very simple, so let's go compute it. We have a equals the definite integral from -2 to 2 of 4x squared minus x to the fourth quantity dx. And so the antiderivative of 4x squared is simply 4x cubed over 3. The antiderivative of x to the fourth is x to the 5 over 5, and all that's to be evaluated between limits -2 and 2. So we begin by substituting in the upper limit 2 everywhere we have an x. So we have 4 times 2 cubed over 3 minus 2 to the fifth divided by 5. And now we put a negative sign, we subtract what we get by putting in -2 everywhere. Well, notice we have odd powers, so putting in -2 is going to give the negative of what we would get by putting in +2. So I'll just put negative, and the same thing as we have right here. 4 times 2 cubed over 3 minus 2 to the fifth over 5. So in effect, negative is positive, and really we've just got twice this one. Alternately, we could have realized that from symmetry, because the integrand here is actually an even function, the integral from -2 to 2, because those limits, what we might call even limits, one is just the negative of the other, the integral from -2 to 2 is simply twice the definite integral from 0 to 2. But in any case, we get 2 times the quantity 4 times 2 cubed over 3 minus 2 to the fifth over 5. Well, notice 4 is 2 squares, so 2 squared times 2 cubed is another 2 to the fifth, so the 2 to the fifths factor out, times 2 is 2 to the sixth, multiplying a third minus a fifth. Well, putting this over a common denominator, we get a 5 minus 3 over 15. 5 minus 3 is another 2, so we end up with 2 to the 7th power divided by 15, which is in fact 128 over 15. Well, sometimes we need to find the area between two graphs when they cross each other, and in fact one is sometimes above the other and sometimes below the other. And so in order to deal with this, we have to find all the crossing points, and let's see why with a picture. For example, in this picture, I have the parabola y equals 4 minus x squared and the straight line y equals -x plus 2. And we'd like to find the area between these two curves, between vertical limits x equal -2 and x equal plus 3. So notice the parabola is sometimes below the line and sometimes above the line, then over here it's back below the line. So what we have to do is break this area up into 3 distinct pieces. Here we have the piece between the limits x equal -2 and x equal -1. There the line is above the parabola, and so we can calculate that area using the definite integral from -2 to -1 of this function, the one on top, minus the one below, which is the parabola. Then from -1 to 2, we have to go the other way. The parabola is on top, so we're going to be computing 4 minus x squared minus -x plus 2 quantity, integrating that from -1 to 2, and then from 2 to 3, The line is back above the parabola, so we're going to be dealing with negative x plus 2 minus quantity 4 minus x squared. Notice we keep having to switch back and forth. In all cases, we're dealing with the difference, 2 minus x minus, and so let's write that down. The difference we're dealing with is 2 minus x minus the quantity 4 minus x squared. And where the parabola is above the line, we actually need to take this difference in the other order. In either case, you can notice that we're dealing with the absolute value of the difference, and that's always the case. When you're trying to find the area between two curves in general, you're dealing with the integral of the absolute value of the difference, and so that would be the general situation. The definite integral, absolute value, f minus g over the x range that you're interested in. But unfortunately, you don't have a nice formula for integrating the absolute value of a function in terms of the function itself, and so consequently, looking at it this way at first doesn't give you any help. You still have to find these breakpoints and integrate from one to the next, and so on. But one thing I'd like to point out is that suppose I had no picture and I didn't know which of these was on top. I just know they cross at -2 and -1, or they cross at -1, and we want to go from -2 to -1. And there is no crossing between -2 and -1. What would happen if I'd have subtracted the negative x plus 2 from the 4 minus x squared? Notice I would be getting the negative of what I want, and so in the end what I would get is the negative of that area instead of the positive. If I did the same going from -1 to 2, I would get the negative of the area instead of the positive. That is, if I subtract in the wrong order, in each case I would get simply the negative of the actual area. And so consequently, once I realize that going from -2 to -1, the difference, integrating the difference in either order is only going to give me the answer up to sign, I know the correct one is to take the positive sign. And so that means what I can do is look at the antiderivative of the difference. In other words, let's look at 2 minus x minus the quantity 4 minus x squared in absolute value. So here is another picture. The area we're interested in is simply the integral from -2 to 3 of the absolute value of the quantity 4 minus x squared minus the quantity 2 minus x dx. And that's integrating from -2 to 3, but to accomplish that, we have to break it here at -1 and at x equals 2. So we go -2 to -1, then -1 to 2, then 2 to 3, and in each case, we just look at the absolute value of the result. Another way to say this is that the area, which is the integral from -2 to 3 of the absolute value of the difference, is simply the integral from -2 to -1 of the integrand, take the absolute value of that result, plus the integral from -1 to 2 of that same integrand and take the absolute value of that result, plus the definite integral from 2 to 3 of that same integrand and take the absolute value of that result. Now this leads to a simpler process which will be computationally less likely to make a mistake. What we do is we just take the definite integral of the difference in any order you choose. So here we've got 2 plus x minus x squared is the resulting difference, and so the antiderivative of 2 is 2x. The antiderivative of x is x squared over 2. The antiderivative of negative x squared is negative x cubed over 3. That's easy. We don't worry about the constant of integration here because we're dealing with a definite integral in reality. And so what we're needing to do is to compute the values of that antiderivative at the left endpoint -2, the right endpoint 3, and at those intermediate breakpoints, in this case -1 and 2. And so we get at -2, the value is 4/6. At -1, the value is -7/6. At 2, the value is 26. At 3, the value is 9/6. So consequently, the area from -2 to -1 would be 4/6 minus a -7/6, which is 11/6. The area from -1 to 2 would be -7/6 minus 26, which is -27/6, but we're only interested in the absolute value, so that gives us 27/6. The area from 2 to 3 is 9/6 minus 26, which is -11/6. Again, we're only interested in the absolute value, so that gives us 11/6. And so now our total area is simply the sum of these three. 11 and 11 is 22, plus 27 is 49. So our total area is 49/6. With this computational procedure, instead of getting involved with trying to keep track of which one is on top and which one is on the bottom at these various places, just take the difference, calculate the antiderivative, then calculate the values of the antiderivatives at the endpoints of the interval of integration and as well at every breakpoint where those two curves crossed. Once you've got the values, you simply take their differences and take the absolute values of those differences from each one to the next, add them all up, and you get the total area between the two curves. Well, there are other situations where we have to break the computation of area into parts. For instance, when dealing with the situations of finding the areas between two curves, and we have to find where the curves cross. That's one place where we have to break it up. But also, we could be dealing with an integrand, which is a function is given by two different equations on various intervals of the domain, or we could be given the problem of finding an area of a region whose boundary is given by different curves, and in some places we have to find the area under one curve, and at other places we have to find the area under a different curve. Well, let's look at an example where this can happen. Find the area of the region in the first quadrant bounded by the line y equal x, the line x equal 2, the curve y equal 1 over x squared, and the x-axis. Well, let's look at just the basic information. We have y equal x equal 2, y equal 1 over x squared, and the x-axis. Notice y equals 0 is the x-axis, and so this is all in the first quadrant that we want to look at. I'll draw a crude sketch here. We'll draw our axes. We have the line y equal x, the diagonal line, x equal 2, that's the vertical line. We have y equals 0, the x-axis. So far we have a triangle, and we have y equal 1 over x squared, which at x equal 1 hits the line y equal x right there, and then comes down. It's a arc coming down here. When x is 2, then x squared is 4, so we get a fourth. So what we're trying to do here is find this area. Notice it is a little ambiguous, and that's why the x-axis is included in the boundary. That is, you might say, if I just said, look at the area enclosed by the curves y equal x, x equal 2, and y equal 1 over x squared, you might think, well, it's this area up here. But the boundary y equals 0, the x-axis tells us that that edge is in the region we're interested in. So here's the region. Notice we're going to find the area from 0 to 1 is just the area of this triangle. That's obviously a half. The next question is, what's this area under the curve y equal 1 over x squared from 1 to 2? You see, we have a natural breaking here of the integral. Alternately, we could say the function we have to integrate here is the function f of x, which is simply equal to x when x is less than or equal to 1, and 1 over x squared when x is bigger than or equal to 1, noting that when x is equal to 1, both of these expressions give the same value. In other words, we have, in reality, a situation where we're simply calculating the area under a curve, but the function itself is not given by a single equation. It's given by two different expressions, each one valid over different parts of the domain. So, in effect, here's our picture then. Here's the y equal 1 over x squared curve shown a little more accurately. Y equals 0, y equal x equal 2, and here's the picture of the area we want to find. So consequently, the integral we want to compute for the area is the integral from 0 to 1 x dx plus the integral from 1 to 2 of 1 over x squared dx. Of course, this is x squared over 2 evaluated from limits 0 and 1. And plus the integral, well, here's x to the negative 2. Its antiderivative is x to negative 1 divided by negative 1, evaluated limits 1 to 2. Of course, this one's a half. We know it's just the area of a triangle. But look what this one is. We're going to get, for the upper limit, negative 1/2, and minus what we get by putting in the lower limit is simply negative 1. Negative a negative 1 is plus 1. 1 minus a half is a half. And so both of these integrals turn out to each be equal to a half. We get a half plus a half, which equals 1. In effect, what this means is that coming back to our picture here, this area shaded is equal to 1. I don't think you would have expected that without computing the integral. The area equals 1. Well, we've worked some problems using substitution and definite integrals and some problems for areas between curves. Now that you've seen these worked, you should try some on your own.